Hello, my name's Casper Abassi, and today we'll be showing ME304 video presentation 2. So first, I'm just going to start off by drawing as best as I can. It's kind of difficult for me. The diagram we are given in this problem. And the problem statement says, for the beam system shown loaded below, find the principal stresses and the maximum shear stress at point H. And it gives us a diameter of 5 centimeters for each cylinder. So our point H is over here, point K here. And this is our Z axis, our X. So we have a beam here, cylinder here, 50 kilonewtons. 15. Okay, and we're given this distance right here to be 2.5. This distance to be 1.5. We know here to here 6 meters. And here to here is about 4 meters. So not a very great representation, but it'll do. And so the first thing we want to do here to make it a little bit easier for us is we're going to kind of write out our position and forces in a 3-dimensional coordinate system, I, J, and K. And this is going to help us find our Rx and our Ry, Rz, in addition to our moments. So we have our 50 kilonewton force, we have our 17 kilonewtons, 9 kilonewtons, and 13 kilonewtons. Yep, okay. So working through this, I's, we just have a J here. 17, so 1.5 in the X, 6J, 0K. This is 0X, 4J, 2.5K, 0. And this is going to be the same as that because it's on the same beam. Now for our forces, let's see. We got, this is an axial guy, 50, 17, 9 here. And, well, we can, either these can be negative or that can be negative. So let's make this negative 0. And this is 13. Okay, so we can see that these we gain just simply by looking at the diagram here. And so the first thing we want to do, I'm going to actually go ahead and I'm going to demonstrate. We're going to need, later in the problem, we're going to need I, a moment of inertia, area, and J. And these are defined as first pi over 4, there's a radius cubed, or no, to the 4th. Just going to calculate that real quick. Now our It's going to be diameter squared. J is going to be pi over 2 c cubed to the 4th, excuse me. That's going to give us okay. So these are going to come in handy later when we are calculating for our bending and axial stresses. So first, what we want to do, let's look at our axial. Oh no, excuse me. No, first we need to, yes. First we need our I'm getting a little ahead of myself. Rx, Ry, and Rz. And so that's going to be -9 in the x. This is going to be 80 for y. And 0. And our moments, moment x, moment y, moment z. First, in the x, we have 13 times 2.5. It's going to be, let's see, in the way this is going to be a negative moment. And that's based off of the way, looking at it on along the x, the yz plane, our moment is going to give us a negative. And then for the y, we have 9, and that's also, yes, times 2.5. Okay. And that's going to be a negative, same reason for the negative, 22.5. And for this guy, I'm going to do 17, and that's the 1.5. Okay. These are all kilonewtons. Okay, now we're going to look at our axial stresses. And so as we can see in our diagram here, the only thing acting on the axis is right here, 50 kilonewtons. So we can call this y, I guess. So this is going to be just simply force over area. So we have 50 kilonewtons over area. It's going to give us 25.5 MPa. And actually, I think now that I'm looking at it, that is going down. So this is going to be negative because that's going down. Yeah. So negative 25.5 for our axial stress. Then we have bending. So in that case, then we can call this x because that's y. We have the equation mc over I, and that's why we have our I value here. And we're gonna use this moment right here because we're looking at it. Basically, this coming down on top of the h, with the point that we're looking at. It's gonna cause it to move basically through this force. So that's why we're using our moment there. That's going to be negative 32.5 times C.25 over I. It's going to give us negative 2,655. Okay. Now we're going to add up we're going to add our bending and moment, or I'm sorry, excuse me, bending and axial stresses here. And by doing that, this is going to be the stress that we're using to find our principal stresses, which makes sense if you think about it. We're using our axial stress plus the bending stress on this point. And I'll note that the reason that we're not using this 17 here at all is because it really doesn't affect point H. Now, if we were looking at point K, it would make more of a difference. It doesn't affect point H because this stress is coming down on top of K, so it would bend K. But because if we look at this from the Z axis, then the 17 is going to be kind of, I guess, parallel planes with the H, so it's not going to affect it. So we have this as our compressive stress. So we can just say this is compressive. Okay. Now we need to look at torsional. And that's going to basically help us find our tau xy, our maximum, not our maximum, but our shear stress here. Not quite at the maximum yet. And that's defined by TC over J. So plugging that in, we have 22.5. And J is going to be 6.13 times 10 to the negative 7. Okay. Calculating that guy. is going to give us a value of 917 MPa. Okay. So we have everything that we need here in order to find our principal stresses and maximum shear stress. And we're going to use that using the equation sigma 1 comma sigma 2 equals sigma x plus sigma y over 2 plus or minus. And this correlates very well to our Morse circle that we have solved before. And I'll note that this is our sigma x here, this sigma right here, and there's no sigma y. So plugging that in, we have negative 268 over 2 plus or minus. Sorry about that. Gonna go ahead and calculate that guy. So this is going to give us our two stresses, which come out to be negative 2,963 or 64. And sigma 2 is going to be 283. And finally, for maximum shear stress, as we can remember from our Morse circle, this is just going to be the average. So calculating the average between these two values, we get a total MPa, 1,640. And I believe that's going to be negative. And these are our final answer. Thank you. I hope you enjoyed the video. Have a great day.